Alright guys, here we go. We got to talk about some absolute value items before moving into functions. So let's wrap it up here, and then you can. I might go through this a little quickly since you'll also have the PowerPoint to read off of. Okay, absolute value implies the distance from the origin on the number line, as we well know. Okay, the absolute value of anything after evaluating its absolute value is always positive. As I'm sure you always know. Okay, here's a big definition for absolute value, and you really got to grasp this. Okay, effectively says that the absolute value of something is either going to be the positive version of that something or the negative version of that something. Okay, and really, I'm probably at fault in what I said right there in saying the negative. I probably should say the opposite. So in other words, the absolute value of A is equal to A, provided that what you're taking the absolute value of, A, is greater than 0. On the other end, if A is less than 0, that is if A is a negative number, then the absolute value of something will give you the opposite of what you give it. So when you give this expression a negative 5, it spits back a positive 5. When you give it a negative 27, it spits back a positive 27. So this definition you cannot take lightly, okay? So it reads, the absolute value of something is that something, provided that something is greater than 0. And the absolute value of something is the opposite of that value, provided that value is less than 0. So this definition will get a lot of mileage out. This is what's called a piecewise description. Notice it does not, the definition does not take hold of 0, but we could put an equals bar in either the top branch or the lower branch. We'll see that, okay? A lot of problems imply this, okay? So, and this is where that definition is going to come in handy. So they want you to rewrite this expression, this absolute x minus 3 plus 1. Rewrite that expression without the absolute value bars for values greater than 3. So here comes the idea. Is values greater than 3 when plugged in here cause this to become positive or negative? If it becomes positive, which in fact it does for any values greater than 3, then the absolute value bars have no bearing at all. So we could just drop them, in which case we do, and we simplify the expression. What about for the same expression for values less than 3? For values less than 3, check a value, 0 per se. 0 is less than 3, so 0 minus 3 is negative 3. So then what happens? You are inside here with a negative, okay, and the absolute value will alter it to a positive. So actually the absolute value is taking its opposite. So for any value less than 3, when placed in here, this expression, this entire x minus 3 expression, will go negative, and the absolute value bars will in effect report its opposite. So we can, for values less than 3, we can drop the absolute value bars at the expense of making this the opposite of what it is, okay? And then doing the algebra, we simplify that down, okay? So here's one now, and we're going to kind of accompany this with a graph as well to illustrate. So for values between negative 3 and 2, what is going on with this expression? Okay, so we pick any value between negative 3 and 2, and 0 is, of course, a convenient value. So when 0 goes into x minus 2, we get a negative 2. And therefore, for any value between negative 3 and 2 and put in here, we will get a negative, okay? Which means the effect of the absolute value bars is to give the opposite of what's inside. For values between negative 3 and 2 going in here, they're always positive, so the absolute value bars have no bearing. So here's how we can rewrite that. So we rewrite that again right here, saying that between -3 and 2, all values going in here will be negative, so we have to take the opposite of x minus 2. All values going in x plus 3 will be positive, so that is left with no impact. So we do the algebra, we tighten up, and we see 5. And here is the graph of that, which is interesting, okay? Because what's it show you? It shows you exactly what this is saying. For values between -3 and 5, this is flat line at that value of 5. So we've typed in this expression, but between the values of -3 and 2, as you can see, we report back to you only 5. Okay? Some properties of absolute values you should acquaint yourself with. Okay? I'm not going to read them off. You go to the PowerPoint and you can read them off yourself. Okay? Here, utilizing those properties to simplify this expression without the absolute value, okay? You should go through that as well, okay? As we said earlier, absolute value does imply distance, so sometimes we have to have a word problem or two in which we can translate that through the absolute values, and here's some of those examples, okay? Absolute value equations are as follows, okay? Anytime you have an absolute value equation, you have to realize that that which is inside the absolute values could, in this instance, be either 12 or -12. So we have to set it up as such and solve accordingly. Okay? And again, this is kind of an algebra review, but again, it's taken all possibilities of the values of x into play here. Okay? So what about absolute value inequalities? Okay? Absolute values inequalities are as follows. If the absolute value of something is less than a, then it implies that you can remove the absolute value bars at the expense of comparing it in this way between a and a's opposite. Okay, so that it reads the opposite of a is less than x, which is less than a. Okay. And for the absolute values of x being greater than, that implies, okay, we compare it to a, and then we compare it to the opposite of a with the opposite comparison. So from this we move to x is greater than a and x is less than the opposite of a. You see some of that as an example. So here is a case in point, okay? Here's a description. It says that the absolute value, or that says that the distance between some number and -2 is less than 8, so the distance is, understood to be the absolute value, and the some number is x, and the distance is the difference between the two coordinates, so the difference between a number and -2 is supposed to be less than 8. That translates into this expression, okay? This, of course, minus the negative goes plus. This less than 8 means that the cost of removing the absolute values is to compare it to 8 and its opposite sandwiched in between. We can subtract 2 on either end, and we get the range of values for which this absolute value, for which this description is defined, okay? For this absolute value expression greater than 5, we have to parse it up. We have to compare it to 5, unaffected, okay? And we compare it to -5. Again, the original expression, unaffected, but comparing it to the opposite with the opposite comparison. Okay, work those out accordingly, and then we are best to report our answers in the interval notation for all values greater than 3 or less than -2. Okay. Here are some further examples. Okay, here's another example with the distance. The distance between x and a number is greater than a half a unit. Okay, again, a greater than absolute value implies the expression with the greater than comparison as if the absolute value bars were not there. On the other hand, the greater than with the absolute value bar is removed is compared to the opposite with the opposite comparison, okay? Some more problems here. The problem B would imply that we add 3 to both sides before breaking it up into two groups. Some expressions to consider, true or false, okay? And you got to read this one. This is kind of tricky, but not if you read it right. The absolute value of A is equal to the opposite of A if A is less than 0. That is by definition, okay? So that is true. The absolute value of A minus B is equal to the absolute value of B minus 8. I think you put some values in there and you'll see that is true. This is reading what? The opposite of the opposite of the opposite, so on and so forth, so you can check the validity of that. This is a true statement, well, one that you should realize we just talked about, as is this a true statement, one which we just talked about, okay? This is pretty much a graphical solution. So this is the absolute value of 2x plus 1 as graphed. This is 5. So we're asking when is it equal to 5? Well, we can kind of pinpoint off where they equal. It's at 2 and at, what's that, -3. Okay. When is it less than 5? Well, it's going to be less than 5 whenever the absolute value is underneath that horizontal line, which is, of course, between -3 and 2. And then it's going to be greater than 5 for, what, 3 on out, for 2 to infinity, and -infinity to 3. It's just a graphical solution to that. Some problems warrant your consideration, okay? Again, for values greater than 3, this is always going to be positive, so we just can rewrite it as x plus 3. For values less than 3, it's always going to be a negative, so the absolute value will cause this expression to be oppositized, if you will. So we would rewrite that as the opposite, parentheses x plus 3, or -x minus 3. Okay, and this is one where combinations, okay, between -6 and 4, 0 is a good test point. 0 goes in there. This whole thing reads as negative, so the cost of removing the absolute values would be to write that as the opposite, and this one could say the same, so we would simplify that from there. And there you have it, a discourse on absolute value expressions.